Now, the next topic, we focus more on a novel deep model based on the word attention mechanism designed for predicting a number of resources an emergency department patient would need. It will be given by Djordje Gligorijevic, whose research interests include large-scale machine learning and data mining, with applications in healthcare and computational advertising. And he is currently employed as a research scientist at Yahoo Research Group. So please give him a big round of applause.
Thank you. So today I will be talking about our model that we implemented, published at SDM conference. So this is also work that was presented a couple of months back on the SDM, so it's really fresh. The algorithm that we built was designed specifically for this task, for automatizing triage of emergency department patients. And it was done with a group of collaborators at Temple University. So just before I start, let me get a little bit of context from you guys. How many of you actually are aware what is triage process? Okay, so very few of you. So I will try to do a little bit of walkthrough of what triage process is. In that case, I will state what is the problem that we are actually trying to solve. I will talk a little bit about the data we have and what kind of data we used. Give you a little bit of modeling background and spend a little bit more time on the way we design our approach, how we develop our model, and talk about the results we obtained. So, triage process works kind of like this. You get sick, you go to the emergency department, and then you get put into a triage room. Triage room, you can imagine it as a room, as a desk, or in a case of Temple University, it's a bulletproof glass tube. Essentially, nurse then tries to assess your severity. She checks for asks you for things like what is your complaint, measures blood pressure, heart rate, and things like that. And based on that, she tries to assess what is your severity. To help nurses do this task as best as they can, American Health Association 15 years ago developed something called Emergency Severity Index, DSC. So it is a tool that works kind of like this. As I said, first we ask, does the patient require immediate life-saving intervention? If it does, it gets assigned ESI level 1. This ESI level 1 means you will automatically be sent into the room, you will get a physician working on you immediately. So we're talking about gunshot wounds, things like that. Then she kind of asks is it a high-risk situation? Is the patient confused? Something like that. If yes, you will be assigned level 2, so next level of severity. If not, nurse try to assess something called how many different resources are needed. Resources in emergency department, you can think of them as anything that goes from consultation with a physician up until any kind of intervention or infusion and things like that. If there are many of resources needed, and if vitals are in danger zone, patient will get level 2. If there is only one resource needed, patient will get level 4, and if there are none resources, patient will get level 5. System worked for 15 years. With one little thing, there is a huge variability in what nurses assess. When we actually go and check the severity ESI levels, or the acuity levels, sometimes we call them as well, we can see that nurses actually go and label most of the patients with level 3. Level 3 essentially means you will be sitting in the waiting room. And from there on, you will be served on first come, first serve basis. Which means that a patient who has internal bleeding that came after a patient that was, for example, had anxiety, will have to be treated after a patient with anxiety, even though they are more urgent. If you take a look at the number of resources ESI acuity level 3 a patient have, we see a lot of people that require 0 or 1 resources only. So these are people that you would ideally place in level 4 or level 5, maybe even send them home. As well, we see a lot of people who have 5 or 4 resource categories needed. This means these are highly severe patients. This variability in people has led to big problems in emergency department rooms. These rooms were overcrowded. These rooms, so there was no good way for physicians to assess which patient should be treated first. And this was a big problem. One of the professors from Temple University came to us with this problem and asked us to try to build a solution for this. What we didn't know at that time was what kind of data we have. And the biggest challenge was that most of the data is written in text format. So the challenge for us was to use these nurses' notes data, the data written during the triage process in the triage room, and try to predict the outcome using an automatic and accurate triage. To do that, we defined two predictive problems. First of being patient severity. Essentially, we want to see if patient is going to need 3 or more resources. So again, please differ between ESI levels and resources. One of the things is what we know is true, which is resources. We know how many resources patient actually had at the end. So this is ground truth. And ESI level is free assessment by the nurse. So we don't know the true ESI level essentially. So this is not something that we know exactly. And second task is a multi-binary classification, multi-class classification, which we try to predict which is the resource class this patient is going to need. So let's talk a little bit about the data we have. We can split the data they collect in emergency departments into 2 separate groups. One of them is structured data. So this is data you most commonly work with. So we're talking about demographics, gender, age group, assigned location of emergency department, method of arrival, hour of arrival, blood pressure, heart rate, temperature, insurance group, everything you can structure in a, let's say, 0, 1, or some other way in a vector. And then the majority of information is actually stored in this unstructured part of data, which is chief complaint, past medical history, medication list, and free text initial nursing assessment. This is where the description of this patient actually comes from. How do we use this data to actually predict how many resources will this patient need, thus achieving some automated triaging process here. The data consists of, in our case, of 3 years of data, totaling about 340,000 emergency department visits. In our split, we essentially use 68,500 patients for test, out of which 36,883 were ESI level 3. So we are mostly focusing on ESI level 3 when we are evaluating. So this is the case where people are stalled in the waiting room and are actually waiting. Again, we are not trying to predict ESI level 1. You have to understand a little bit about the business case here. So if a patient comes bleeding, they will have to be assessed. The biggest problem here is are the patients that are stalled in the waiting room. And we are trying to rank them as well. So, as I said, there is plenty of text data here. There are no good ways, there are no de facto good solutions to how to treat, how to model text data. And in order to do that, we had to look a little bit back about what the research communities has given us. The first thing I want to show you and talk a little bit briefly about is our low-dimensional embedding layer. So these are models that do one simple thing. Try to represent an item or a word in a vector of numbers. For example, word king will be a vector of numbers, word queen will be a vector of numbers, and so on. And ideally, each position in this vector will represent something, like royalty, masculinity, femininity. And also, once we plot these vectors in some space, for example, 3D space here, we expect them to retain some kind of geometry. So relation between man and woman should be similar to the relation between king and queen. If we can achieve something like this, that means we capture some kind of innate structure in the data. These kind of models, when we talk about deep learning in particular, were initially proposed by Benji et al. In 2003 with a classical language, neural language model, and have been more popularized recently by work of Colbert Weston and Mikolov et al. With his word-to-vec algorithm presented in 2013. Next thing, after we know that we can actually represent words as a vector in low-dimensional space, we had to know how to capture sequence of data. So as you know, text is something that's written in a sequence. And a great tool that we already have for modeling sequences are recurrent neural networks. They essentially look at a sequence of data, look at the input, and each word or each item in the sequence, its representation is dependent on its input, so the current word, and all previous words. RNNs, as they are, work phenomenal. For any textbook example you can give it. We have a little bit of a problem in a nursing assessment. Nurses write things really quickly, really dirty. They repeat stuff. They make typos. They reconnect things in the document across the whole document. This is really hard data to work with. This is not Shakespeare text. In this case, we need to go a little bit more than just modeling left to right. We need to reconnect every single word to every single other word using modeling techniques. A good way that achieves that are bidirectional recurrent neural networks. Really simple extension to traditional neural networks. We send one neural network to go left to right. We send another network to go right to left. And essentially like that, each two words will be dependent on each other. And we can use their stacked representations to predict. Finally, what I want to mention are LSTMs, or long short-term memory networks. These are nothing but extension of traditional recurrent neural networks, nothing too fancy, except they solve two huge problems of RNNs, exploding and vanishing gradients. You can think of them as one simple extension with a hack that solves some numerical computation problem. That's it. Once we know all of this necessary background, at least from a deep learning point of view, I can talk a little bit more about the algorithm we designed. And here it is. The algorithm we designed is a deep learning algorithm. It consists of three major blocks: the text embedding block, the block that should capture the information from the nurse assessments from text itself, the attention block. This is what we proposed as a contribution in our work, and the final classification block that performs simple classification. You can think of this as simple multi-layer perceptron. So going top to bottom to top, we first embed words into low-dimensional space. We apply linear projection of nodes. This is essentially, this helped us improve a little bit more. So this is like some of those hackish things you do with deep learning. You apply certain layers to see if it helps or not. Our intuition was that words are super interleaved with each other, that we simply need to like connect them is essentially in a cross-feature way. So that's why we apply simple linear projection nodes, after which we apply our BLSTM layer that learns dependencies of all words amongst other, and then we apply one more linear projection of nodes, essentially to decrease the dimensionality for purposes of speeding up the algorithm, nothing else. Attention layer is used here to summarize, essentially. This dimension are words in the document. This dimension here are embedding size. So each word will be assigned, let's say, 50-dimensional space, 50-dimensional vector. And what we like, in a nutshell, what we like in machine learning is to work with vectors, not matrices. We want to summarize this matrix into a vector. How do we do that? I'll go to the next slide and talk a little bit about that. Summarization of text has been given a lot of attention in 2017 and 2018 in the research communities. There is no de facto good way, and this is what we believe is currently the best way that we know we can do to summarize text. So first, to recap of what we can do is, once we get that representation of multiple words, each word has its own vector, we can select max vector, something like max pooling in CNN that was proposed a while ago. We can do sum of the vectors, so sum all the vectors, and this is actually essentially working really good. We can average them out, we can product them, and so on. We can do multiple things in how can we actually define this summarization. None of them work really, really good. And always, there are always issues. Sometimes one of them works better than the other, sometimes the other one better than the first one. We have a little bit of issues in consistency there. Essentially, in our data, we figured out that out of these, some simple summation of all hidden vectors of each word I is what works the best out of these previous proposals. What we propose then is to use an attention layer. Attention layer is, again, really simple technique. It's a separate neural network that does nothing but feeds on the very representations of words and learns their attentions. Attentions are simple logic scores coming out of the softmax function. Essentially, every word will get assigned a value between 0 and 1, and summation of all attentions across all words will be 1. So you know how much information can be fed for each layer. What we propose then, instead of using simple summation, is to do a weighted summations, where a weight of each word will be its attention. The word that has bigger attention will feed its information upstream in the algorithm. The word that has less attention will feed less information. Simple as that, but very effective. And there is one more thing. I talked about that we have a lot of structured data. And this is something that also became really popular in the last year, something called deep and wide models. Industries across the world have applied machine learning for decades now, different techniques, and scientists have built a lot of features that are really, really useful. Now we have deep learning that kind of like builds features on its own, doesn't really need. It's also really competitive to these features that were built over decades. But if you use both, we can perform the best. In our case, after learning the representation of nodes, we can stack and simply append the structured Y features that we build from the rest of the data we have, thus hopefully yielding the best result we can obtain. And now let's talk a little bit about how this model actually works, how it performs, and answer a couple of research questions. To evaluate our model, we ran a couple of standard baselines. We first used baselines that used only structured data, these are simple logistic regression and MLP. And we ran a couple of state-of-the-art algorithms that capture information from the text, bidirectional LSTM model, word level CNN model. This one became really, really popular in 2017. I still consider one of the state-of-the-art algorithms. It works really fast given it's CNN algorithm. And finally, we compared to the algorithm that's the same as R, but does some polling instead of the attention. We just want to see the effect of the attention, how much it helps in the actual prediction quality. So let's start answering some research questions. So first research question we can ask ourselves is the text data even useful? So we do measure heart pressure, we measure temperature, we measure all of these things. Is text even useful there? Well, once we compare logistic regression and MLP on our task, we can see that their results are not that great. 50 to 26 on AOC is not something you really like to see. 50 is like the baseline, that's like random. Our model, using only unstructured data, outperforms it severely. And once we add structured and unstructured data into our DAM model, we can see it's almost constantly outperforming. AOC is something that we usually want to look at. Accuracy is something you can tweak a little bit depending on your threshold. So in AOC, you can see that the DAM with both PU and PS, so unstructured and structured data works the best. Next question is, can we narrow down to the tasks of binary classification? So just trying to guess whether a patient is really severe case or not severe case. And second task is, can we actually guess if a patient, which category of resources a patient is going to need. And what we did here, we compared it against state-of-the-art deep learning models. We can see that our DAM model for both PU and PS, so structured and unstructured data, was able to outperform all of the deep learning baselines on both accuracy and AUC. On the task of multi-class classification, so trying to guess the actual number of resource categories, we can see that our model is still the best. Numbers usually drop when you try to predict across multiple targets. So when you do multi-class classification, so it's quite normal. Usually you want to have the relative improvement over state of the art, which you achieve. And then it comes to the most important question of all. How does this algorithm compare against nurses? So we have this machine learning algorithms developed over decades. They work really well, but what happens when you bid them against humans? So this is like actual nurses who were educated for years to perform this task, and this is algorithm that was training for 20 minutes. Now, coming back again, how can we evaluate this? Obvious way is to do A/B tests, run one shift with our algorithm, run the other shift with nurses. Obviously, there are so many ethical questions there, so we couldn't run something like that. We had to do retrospective analysis. And as we said before, we have two things. We have acuity levels, which are ESI levels, and we have number of resource category. So in order to guess which level patient is, nurses have to guess which resource category is. But they don't write that in a document. We just know the actual outcome at the end of the stay. So in order to map between what was the guess of acuity level and what was the resource category actual guess, we used this little table that we defined with 3 professors from the emergency department at Temple University. And we were able to build this confusion matrix here. Once again, we remove level 1 because level 1 are patients. They simply go into the room. There are absolutely no questions there. They go inside the room, they get treated immediately. So we are not interested in terms of modeling these patients. Using this confusion matrix here, we can see that what nurses obtained as overall accuracy is 43.62%. What our algorithm performs on the same matrix is 59.61. 16% of improvement over state-of-the-art, over human performance. Our algorithm was actually being able to outperform human performance in this task. And this was really, really exciting results. One more thing that needs to be answered in the end is, can this algorithm be implemented? What does it mean for algorithm to be implemented? Can we just allow an algorithm casually run around and send people to either rooms or waiting room or send them home? Well, not really. There are a lot of ethical issues, and above all, we have to make it through the biggest stepping stone, which is management, hospital management. In order to do that, we have to make our algorithms interpretable. And this is where actual reason why we are using attention comes in. Our attentions were able to highlight words in a document, in a nurse assessment document, that are actually biggest reason, that are actually driving the reason behind predictions. So you can see in a couple of examples here, for example, motor vehicle collision, or MVC, which is again motor vehicle collision. Our algorithm placed the biggest attention on the word collision, lowering the attention of word MVC because MVC is nothing but short of motor vehicle collision. We can see in a second example that pain is again big, has assigned big attention, or can you see it from here? All right, here. I totally forgot about these examples. Or chest pain, gunshot. Okay, gunshot. Great. I know there was a gunshot example there. So obviously, gunshot is a huge, huge feature that you want to look at when you admit someone into the emergency department. Having this as an output of an algorithm while the triage runs is something that can help nurses use these decisions made by the algorithm, help them standardize their decisions. So as we remember, we have multiple nurses. One nurse is traditional, sends everyone home. Other nurse sends everyone to waiting room. Third nurse sends everyone into emergency department rooms, like overcrowding doctors. Using algorithms like this can help us standardize this process, ideally save lives down the line. So to summarize what we achieved here, so we addressed the problem of high variance subjective resource utilization outcomes prediction in triage process. We were able to utilize text data, that free text data from the nurses. We were to propose a model that beat state-of-the-art accuracy across state-of-the-art algorithms as well as human performance. And we were able to show that this algorithm is, above all, explainable. We know why it makes predictions, and we can implement it in actual systems. And with that, I would like to conclude this talk. The code for the algorithm, not the data, is available at this link here. if you like, you can play around with it. It works really good, not just for emergency department data. You can like run any kind of text data that you guys like. There is an example there. So if you end up using it, feel free to shoot me an email anytime. I'm happy to like help and answer any questions, as well as any questions now. Thank you.
Thank you. Just a reminder to use the link dsc.networks/Q/A/Tesla with a capital T. Moving on to the questions. The first question we have is, how would you solve human text input errors for the structuralization of data for further analysis?
That's actually a really good question. So we end up running multiple pipelines there. If you know, for example, a nurse can say, hey, this patient drank ibuprofen 200 milligrams, ibuprofen 300 milligrams. There are also, that's one problem. Another problem are typos. What we did for typos, we tried to canonicalize them as best as we could. We ran some simple data feed processing. So this was not done extensively because the research was mostly focused on proposing an algorithm. So there is a better job that can be done on just cleaning up the data. But we did clean up, we did canonicalize, so resolving the problems of typos. We did learn phrases. So phrases will be, one phrase will be, let's say, ibuprofen 200 milligrams, ibuprofen 300 milligrams, represented as a single word rather than as two separate words to help algorithm like clear up this data. And nothing more, just cleaning standard cleaning, text cleaning algorithms, nothing too fancy that was done. Definitely more can be done in just cleaning up the data and just feeding more clean data into the algorithm, definitely.
So going back on a different topic a bit, why do you think that summarization has the best performance with regards to the algorithm up there, rather than the average amount, the product, or so on?
So as we saw, like in example, couple of examples here. So if we use simple summation rather than the average or the average rather than weighted average, this MVC, which is redundant, would have same level of impact as the other words. Having this like way is able to clean up data a little bit and actually emphasize on certain keywords. So there is a lot of repetition. So we'll have like patient space PT space something something. Patient and PT means the same thing. And the nurses, just because of the speed, will just write. So they are like trying to write this down as they are asking patient for what their complaint is.
Quite nice. So what do you think? How much can you actually compromise the speed of the algorithm to gain effectiveness?
So
in the end?
That's a good question. So deep learning algorithms are notably slow. We were lucky enough to run this algorithm on the really high-end machines. Training was done in less than 20 minutes. Execution is done within a couple of seconds. Unlike serving online results, like results of web queries or trying to guess which ad the user is going to like, you can take a couple of seconds to actually make a decision rather than having a couple of milliseconds. So deep learning actually doesn't have too much of an issue of being deployed in real runtime as opposed to some other industries. So.
Thank you. And here's one. So do you use nurse histories when talking about the algorithm? Do you take into account?
Can you come again?
The nurse histories. Do you have some background information on that, or?
So essentially, no. We don't. We try to avoid using any information about the nurses, ethical issues. Essentially, you don't want to know too much, and you don't want to be able to highlight, hey, this nurse is really bad. Getting nurses employed is hard enough, so they try not to go into that at all.
Sticking with the nurses topic, what do you think? Would your algorithm in the not so distant or distant future completely eliminate the need for nurses in this triage, or is there a need for this human factor there?
I like this question. So I'm trying to come up with a short answer. You have to be really, really careful not to oversell things. As far as this algorithm goes, it depends on nurses' text as input. Without nurses, it cannot run. Maybe in a distant future, we can have some machine that makes a good render scan of patient as it comes, eliminating nurse. It's still not there yet. So we don't have this technology first. And going about and promising that we can just eliminate nurses really quickly can lead to overselling, which can potentially lead us to another AI winter. And we kind of don't want to have that. So we are really, really careful about how you sell things. So that's a general rule, I guess.
Thank you. And I have a couple more, one final one, let's say. With your algorithm, in which other areas of work do you see them being most used in terms of, apart from the emergency department, which other areas do you see it being most effective, most useful?
So actually, there are a ton. Wherever you have text data, you can essentially run this algorithm. The example I plugged in for the runtime on the actual code on GitHub was Amazon reviews. For example, you have a review of your, the description of your product, and you want to guess what is the average review is going to be. And based on that, you can try to alter. For example, that's one example. But you can go wherever you essentially have data.
Oh, well, quite
like that. Yeah.
Quite universal then. Okay, that will be it for these questions. I would like to thank you, Djordje, for giving such a talk.
Thank you.
And to also give you the certificate of appreciation on behalf of the conference.
Thank you.